Good morning, everybody. Welcome to today's ARC web window on the industrial edge. My name is David Humphrey, and I have the pleasure of sharing some thoughts and ideas on the developing industrial edge with you for about the next 30 minutes. I'm going to try to keep it to 30 minutes today. I have 19 slides. My view in the online world is that everything can be done shorter. So what used to be a half an hour time slot can easily be compressed to 20 or 25 minutes. Let's see how well we do today. What I want to cover today basically are these points. I'm going to briefly share our definition of what we think the edge is. There's a lot of different definitions out there, and I don't like to dwell too long on definitions. I'm going to cover a number of industrial edge use cases, a couple of examples where I see potential, and probably some of you are seeing the first applications now using the edge. I want to talk about a couple of market growth drivers. These growth drivers are from various market studies on the topic. So these are just factors that are helping suppliers to sell products and users to adapt those products. Some drivers are, there are also some inhibitors as well that are slowing down the progress. Some of the old notions we have about being conservative in the industrial world. The industrial edge's value proposition is, in my view, where I think there's value in investing in the industrial edge. I then want to touch on one of my favorite pet projects, how I think automation architectures will look in the future and how the edge, or what role the edge plays in these future automation architectures. I'll then summarize, and then I'll do a commercial where I'll advertise some of the ARC studies on the topic that you are very welcome to purchase or find out more information about. The industrial edge, people talk about the edge and they talk about the cloud. People ask, are they related? Does one support the other? Are they competing concepts? Are they competing technologies? Actually, they go hand in hand. They're very related. You can do edge without the cloud. You can do cloud without the edge, but in the future, solutions, more IT-like solutions in industrial environments will probably have elements of both. Cloud computing is essentially replacing enterprise data centers. There are fewer and fewer companies, manufacturing companies, commercial companies, doesn't matter, that actually have their own data centers where they employ their own people, their own IT admins, where they purchase computer hardware, networking equipment, and run them themselves. The model is clearly moving to a third-party model where everything is done in the cloud. Smaller companies have long since moved in that direction. Manufacturing companies will also gradually see the advantage of putting the valuable data and collection and management of your data into the hands of people who can probably do it better than your own people, because they do it for a lot of people, and they can scale up to cover the needs and requirements of a lot of users and share that experience, that valuable experience, with individual clients. It's clear for many years now that what we call IoT, or I sometimes call commercial information technology, is influencing the world of automation. For too long, our systems in the industrial world have been closed, have been not very connectable. They've had Ethernet ports for a decade and a half now, that's clear, but we haven't really done a good job of integrating our world into the rest of the world, but that's changing. The edge is enabling a number of applications. I'll get to those in my use cases. I mentioned here analytics, but also machine learning, but enabling these right at the machine level. And finally, it's supporting applications that I think are long overdue in the plant, like augmented, mixed, or virtual reality. They're adding a degree of practicality to these applications. So what is the definition of industrial edge? I don't think we've been talking about the edge for more than 4 years. It seems like about 4 years ago when we first started to borrow the term edge from the rest of the IT world. We came out with an initial definition back then, 3 or 4 years ago, and we just recently updated it to fit in with a number of new studies on the topic. That's why we call this year Edge 2.0 definition. The industrial edge is clearly, I don't want to dwell on this again, like I said, it's a place where things meet. It's where IT meets OT. It's where the physical world in the plant comes together, the machines, the controllers, the software, and it interacts with the devices that connect these things to the rest of the world. So the infrastructure, the IT infrastructure at the edge. Just to be clear, we're talking about things that are not inside the cloud. We're also talking about things that are not in data centers. We're doing a study on industrial edge servers right now, and we're trying to make it clear to suppliers that we're talking about an edge server that is deployed right on the machine and not in a nearby computer room or in a distant data center. And finally, edge systems they're on premise, but they're usually on machine. They're very close, and they are distinct and not the same as what we call traditional automation systems that might have an Ethernet port, like I mentioned before. Edge systems are what actually connect those systems, like I said before. Let's move on to the real world. This illustrates what I was talking about, where IT meets OT. In the middle, you see the typical ruggedized network infrastructure devices. I say ruggedized because for it to be qualified as a product for the industrial edge, it's got to be ruggedized in some way. And finally, what they do is they connect the dumb devices, the devices at the bottom that never grew up in a connected world, the individual sensors, the field devices, controllers, sometimes entire machines. These are what we call the endpoint devices. Here's two scenarios that show what we do today and what we'd like to do in the future. Obviously, to connect the old world to the new world, we need this whole infrastructure that is the industrial edge. These are the devices that connect the old world. Ideally, in the future, we'd have the picture on the right where everything is connected within the machine, and that machine can be connected directly to the cloud. So you could call it machine to cloud, edge to cloud, whatever you like. In the meantime, we need the infrastructure to make these things happen. That's why we're talking today about the industrial edge. So let me just dwell briefly on the topic of this is not competition, automation versus the edge. My assumption here is that we're dealing with traditional control systems like a PLC system with devices connected to it, from I/O to sensors to anything on the local network. Also operator panels and maybe some IPCs, certainly drives and motion controllers. These devices for years, as I have pointed out, have had connectability, but it hasn't been the type of connectability that the rest of the world is used to. Perfect connectability, easy integration, adherence to ubiquitous standards. We like to create our own standards and our own ways of integrating the industrial world, and that has just made it more difficult over the years. So the edge creates that missing IT environment that you don't have with traditional automation systems. Anything that I mentioned before is technically not part of the edge. It's what the edge connects to. These are endpoint devices. What we see out in the market is clearly that automation systems are moving in this direction. They're becoming what I like to call more IT-like. They've been sort of IT-like for a long time, but it's getting better. A good example of this is what I just vaguely labeled right here in this corner, an edge controller. We just completed a market study on any type of industrial controller, from DCS to motion controller to PLC, that meets a certain definition from us that qualifies it as an edge controller. It has to have connectivity, it has to have the physical hardware present, but it also has to be able to send messages not just by traditional industrial networks. It has to master protocols like MQTT, the IT things that we're borrowing more and more that can connect the data in an edge controller directly to an app running in the cloud, as an example. What will future automation architectures look like? I'm going to take a look at those in about 4 slides from now. But in the meantime, let's just examine a couple of use cases. Clearly, the industrial edge is the breeding ground, is the perfect environment for anything having to do with analytics. I like to just say everything has got to be analytics, because what other reason is there to gather all those data that have been there in the past but have been difficult to access, difficult to gather, difficult to analyze. Analyze is analytics, but analytics can be any sort of application. It's usually very technical and very closely related with the type of product you're manufacturing. So I've listed a couple of things here. The first one is condition-based monitoring. It's not really an application. It's more of a technology that enables certain applications. So this is sort of a mix of different terms here. Condition-based monitoring is classic products that have been around for a long time. They tend to be standalone systems. They tend to be not very well integrated, and they tend to be very application specific. So there's no one single solution for condition-based monitoring. There are solutions for everybody's favorite, for vibration analysis. Clearly, anytime you have an expensive piece of equipment that is rotating or moving, driven by servo axis or AC drives and motors, you have ball bearings, and those ball bearings take on a lot of load. They have to be maintained at a certain interval. And the best way to find out what's happening right now with those ball bearings or any part of the rotating or moving hardware is to measure vibration if you can. I listed a number of other technologies here from infrared through ultrasonic analysis, and then very specific things like oil analysis. Corrosion is another one. These are all very, very product specific and very industry specific, but all of them can be monitored in what we like to collectively call a condition-based monitoring system. What does the edge do? Well, the edge helps connect those to the rest of the world, assuming that they don't have this perfect connectivity, assuming that they're not an edge condition-based monitor, for example, which I haven't seen a good example of yet. So once we have all these data collected locally, what do we do with them? Well, we analyze them locally, or we send complete results or partial results to another place for analysis. These data can be used to support quality assurance. And quality assurance is related to the product. So if you're creating a product, then you constantly weigh each individual product, and you look for variation in the weight of the product going into each package or the fill level of each bottle. You can also measure the properties, a certain quality of chemicals with quality assurance. Quality assurance can also be used to ensure quality by measuring stress or changes in the anatomy of the machine. So machines suffer wear and tear, and the actual machine can be monitored as well using devices connected to edge systems. Finally, for this one slide, I talk about the two what have become classics now. Certainly, in order to conduct predictive maintenance, to monitor in real time and wait for changes that can predict impending failures, predictive maintenance is a clear target application of any place where you can collect real-time data to support it, and that's what edge computing allows. And I mentioned here prescriptive as well. Prescriptive is the next stage of after predictive. It not only monitors and detects, it also prescribes specific remedies on how to solve the problem. It makes suggestions, often based on artificial intelligence, as to how to proceed and how to best solve the problem. Let's take a look at a couple of other applications. I grouped these two together. We always talk about augmented reality and virtual reality together, even though they're two very different things. Augmented reality is the guy walking around with the goggles, and where he sees the physical world, but his view is augmented by additional information. Augmented reality has been around for a while. You see it in idealized pictures like the one below, and you see it in some pilot applications. I don't see it a lot in general use. I would have expected it to come into vogue some years ago, but edge computing can certainly augmented reality, because augmented reality lives and dies from very real-time process data that come right from the machine. So if we can gather those machine data, process them quickly, send them to the application that supports augmented reality, then you have a real killer application for maintenance personnel, where they see the real world and they see exactly what is to do and where problems lie, and they have data that they would have to otherwise access from, let's say, operator panels or measuring things. They have those right at their disposal within their field of vision. Virtual reality is the opposite of reality. It's fake. It's actually not real. Virtuality is the video game of the industry. And virtual reality, there's some great applications out there that guide maintenance personnel through simulated plants, through simulated activities like complex maintenance or repair steps, or setting up machines to run a new product, for example. Virtual reality is a great saver in time. The software is not cheap, but it avoids sending your people for training purposes, for example, into not just complex environments, but also into hazardous environments. What you want to do is train them first and then send them into such environments, and not the other way around. And finally, I mentioned precision monitoring control. This is a wide area of application, but the idea is that on multiple machines, multiple lines, even across multiple plants, the concept of gathering and sharing and coordinating the activities of the machines on a large scale based on a lot of locally generated and optimized data. I mentioned before, these are some of the drivers that we see if you're selling a product for the industrial edge. You might be interested in understanding the market through these drivers and inhibitors. I won't dwell on them for a long time, but in my view, the value proposition, which I'll get to my own slide shortly, is pretty clear for manufacturers. There's one thing about the edge is it's not difficult to understand. It's also not difficult to implement. Certainly, machine builders and integrators will include more edge applications in the future, but there's a lot of great opportunities for end users to experiment and to gain that knowledge of how to add analytics via edge computing to machinery that is already out there on the plant floor, already running, and machinery that could benefit by having some additional analytics to understand the process better and maybe to save on maintenance costs by predicting impending problems rather than waiting for something to happen. There's a bunch of other drivers. Let's just go look to the other side, to the inhibitors. In our industry, we're conservative, so we're always bogged down by the slow adoption rate of new things, cloud computing, Industry 4.0, etc. A lot of users need a lot of convincing, a need of a proof of concept before investing in anything. Another problem is the lacking IT skills. We see this again and again, that machine builders and users, it's not that they don't have the personnel in the plant with certain IT skills. It's more that they can't recruit them. It's hard to find people with good IT skills, especially if you're a machine builder located somewhere in remote parts of I'll say southern Germany, where I am right now, in a machine factory, not located closely to a major metropolis where young people with good skills want to live and work. It's very difficult. And let's just move down to the last one. It's my favorite here. Inhibitor is we're waiting for 5G. Why should we do anything on the edge when 5G is coming? Obviously, that's not entirely correct. I'll mention 5G in a couple of slides upcoming. I promised my view of the value proposition of the industrial edge at the very beginning. Obviously, it's an enabler of anything surrounding analytics, and analytics can do wonders for machine operation, for plant efficiency, for plant optimization. I talked about some examples. The industrial edge also bridges our existing world of legacy automation systems by adding this new modern IT environment that enables and modernizes things, brings them up to the level where we can start doing interesting things with our machines and our processes. And I mentioned before, edge computing really does go hand in hand with cloud-based apps. There are some apps that have an edge component and a cloud component. You can do some analysis in the cloud, but sometimes it's better to have a quicker, more real-time analysis right at the edge rather than sending data to the cloud and back. And sometimes it's the opposite. If you're dealing with a huge amount of data, you're not going to want to deal with that at the edge. Or if you're dealing with data from many, many machines, it's better to consolidate these data and compare them in the cloud and see what happens. Now I'm going to stray a little bit into the future. This is one of my pet projects at ARC that I've been following and developing for a number of years. If we look at a typical line architecture, we see the industrial edge. We see individual machines, and if I change my cursor to my pointer, it's called to a pen, then we can see what we typically have today. This, for example, might be, I'll call it the scope of delivery of one machine builder. The scope of delivery of the next machine builder might be this part, and so on. What happens is that each machine builder builds his machine, sends it to the end user for final assembly and for integration with the rest of the line. And the integration, going back to 1995, was this cable right here. By the color of it, it could be Profibus, it could also be DeviceNet or another, any Modbus sort of network from back then. But let's see how far we've come in 25 years. Watch the slide carefully as I change it. Oh, right here. There we go. So automation architectures today. Wait, I'll go back. That was 1995. And if we go to today, what's changed is the color of the cable. We now have green cable, sometimes yellow. And what I'm implying is that we've changed the old networks for industrial Ethernet, thinking that's the solution to the problems of our connectivity and our integration. basically not a lot has changed. The scope of the delivery of each machine builder is still roughly the same. One machine or several machines, each has its PLC, each has an operator panel. The devices right here, let me go back a slide right here. These are industrial PCs, and they're sometimes delivered with a machine to run custom software. This could be for the machine data gathering software. This could be quality assurance for the particular machine operation, not for the entire line. At the extreme left here, I've got what I'll call a line PC, and this might be used to coordinate certain actions in the line. It also might be used to run, for example, MES, a more modern version of the spreadsheet that also became popular at the time, the late 1990s. Going to today's architecture, what could a future architecture look like, and how does that affect the edge? I mentioned before that the OEMs deliver their entire scope so that they can prove that it works at the site, and then they leave. And it's up to the integrator to share the few bits and bytes of information between the individual machines. What if we replaced at the left-hand side here, what if we replaced that line computer with a properly managed IT system of modern quality, using modern IT personnel to ensure the availability of information and computing power, to ensure the integrity of the data that are stored there, and to manage the software? How often have we seen how poorly plant floor software is managed with version management? If it exists, nobody likes to change or update software on a machine. We don't know what's going to happen. We don't know what the repercussions are. So we tend to leave it, and software is not well managed on the plant floor. But what if we took all of those level 2 or level 3 applications, like I mentioned before, and took them off the plant floor and put them all onto what I'll call here a plant server? This could be a cloud, but a cloud on the premises. Let's just call it a plant server or a plant cloud. And instead of the automation people, the automation engineers who take care of the machinery operation, managing the software, we put the management into the hands of people who know what they're doing with software. In other words, IT people that have a good understanding for industrial machines and the dangers of updates and other problems with dealing with software, but are in a better position to manage it. This, if I were running the plant, would be my ideal solution. How do I get, unlike software, to run on the same system? The IT people solved that years ago. It's called virtualization. I can create a container to run my particular application. It runs on the same hardware base, and it has a much better chance of communicating with other devices or software and being integrated because it's all in more or less the same environment. Now, what if we went one step further? And I used to not even show this slide because this was too much for some people. What if we took the PLCs off the machine? Why don't we just, we've had software PLCs, soft PLCs since about the same time, 1995. So why not simply consolidate them on a centralized, well-managed piece of server hardware and take them off the machine? Well, obviously it causes problem. The machine builder wants his PLC. He wants to be able to prove, he needs to test it in his own factory. He needs to prove that it works when he delivers it. But there are ways around this. There are ways really of working with a virtualized PLC that runs a machine, regardless of where it's located, whether it's being tested during startup or whatever. This is a step too far for some, but I saw a presentation last year from Audi where they said this is the future. We're going this direction. We're studying this right now. We've got pilots running. This is not future technology. We're doing this now, and we're trying to understand where the value is for us and where it makes sense to do it. If I clean up the picture a little bit, then we have sort of today's picture. We could have everything integrated. Well, not today's, if we were an ideal version of today. Everything consolidated on my hardware on the left-hand side. And I've stripped the machines of pretty much everything here. What I've left on the machines are the sensors and the actuators. We still need those. I've left all the servos and the drives, so there's still plenty of equipment to put into the electrical cabinets. Don't think it's all being consolidated. But the actual intelligence for everything, why not just communicate with the rest of the plant via gigabit Ethernet, for example, with new things like TSN? Or in the very near future, what if we take away the black cable and just replace it with this fog that we're going to call industrial 5G in the form of a private network? This is something that is definitely coming. This is wireless for the factory that has nothing to do with the little bit of wireless that we might have used today, whether it's 4G, LTE. There are some applications of industrial applications of 4G for certain communications between machinery that it's a preferred solution under certain circumstances to Wi-Fi, for example. Nobody really uses it for control purposes. It's all for monitoring, sharing of data. But what if we left the components we need on the machine? We could even leave in the PLC in the machine. It doesn't necessarily have to all be consolidated. But what if we got rid of the cables? Then our industrial edge is going to look a little bit different today. We can still have the computing power in the form of an edge controller, for example, what this might be with an operator panel. But we eliminate the cabling and replace it with an extremely reliable and extremely high-performing, high-bandwidth technology like 5G with a latency that we can accept. And I talk about a latency in the range of 1 to 2 milliseconds, which is a typical latency that we're used to in the factory. Microseconds is possible in certain things like really fast Ethernet, but for most applications and for closed-loop control, a latency of 1 to 2 milliseconds is really not bad. The benefits of such an architecture, some are obvious. Lower capital costs. I don't have to buy the expensive stuff. I can buy at least partially more commercial style or commercial grade hardware. I can greatly reduce my maintenance costs because I have less hardware and because I put the management of software into the hands of people who understand software, all on a consolidated platform. And hey, it's easier to implement cybersecurity, so why not? So let me just sum up. The industrial edge, I like to say it's not emerging, it's here. There are products or solutions out there. It's ready to be used. It's ready to be tested by end users, by machine builders. There's nothing to wait for, like automated driving, for example, we're still waiting for. The industrial edge doesn't compete with the cloud. It really goes hand in hand. And the future, like I said, will probably be a hybrid solution of both cloud and edge solutions. The industrial edge requires a rethinking of the way we manage our IT systems and software, how we deploy them, how we allocate resources, how we ensure certain levels of performance, and certainly how we manage updates of software. And finally, I just want to say that this is the big step. The industrial edge is currently forever changing automation through the ever-growing influence of IT and OT. Now, I promised you a commercial. If you don't want to buy anything, then you can tune off because it's about lunchtime. But I just put up a quick list here of the studies that we've currently published that cover the industrial edge. I'll point out, for example, just two. I can actually use the pen. Studies like that I find really interesting are the TAM studies. This is total addressable market. These are roll-up studies that give you the entire market size in terms of sales volume and also units or endpoint connections for a whole variety of edge infrastructure. For example, if you don't want to buy individual studies and take a deep dive, then these studies are interesting as well because they're very good for investors or for companies that need to size up the potential for their own product. That is all I have to say today. Thanks very much for attending, and I look forward to greeting you in one of our upcoming ARC web windows. Thanks very much, and goodbye.